Yeah, so good morning. I'm Arnau Bennassar, working at Polygon Hermes, and we are with building a zkEVM rollup that it's compatible at opcode level. And today I'm going to talk about consensus for rollups. Yeah, so I'm not going to fully explain what a zk rollup is, but let's go through some basics just for the sake of this presentation. So essentially, a zk rollup, it's a smart contract on layer 1 on Ethereum. And this smart contract holds the different blocks that we actually call them batches to not create a further confusion. And so these batches contain basically a list of transactions and then a root. And the root is basically a hash of, so like the entire state compressed into a tiny amount of data. But then again, like the main idea of rollups is to do not have to execute the transactions on layer 1. And so that's why we have the zero-knowledge proofs, which actually take the previous root or the previous state and demonstrates the outcome of processing the transaction list. And hence, the layer 1 can trust that the root is actually corrected, processed correctly. Yeah, so how are those batches added into the layer 1? So definitely we need an entity that we call the rollup operator. And this operator basically collects the different transactions from the different users, like the layer 2 transactions. It builds a sequence, like it orders the transactions into a specific sorting. And then it generates this zero-knowledge proof. Once we have that, we just have to send to the layer 1 the zero-knowledge proof and the transaction list. And so this is how a new batch is added. And while this sounds pretty nice, it actually has some problems that I'm just going to explain now. So first of all, this is quite slow because generating zero-knowledge proofs, it's very intensive in terms of computers. And even if you have a huge machine, it will take some time. Hopefully, technology will get better and it will get faster, but still, definitely, we are talking about of minutes in order, like in time scale. The other tasks are relatively fast. So it's basically building the zero-knowledge proof and sending the layer 1 transaction. And then it's very easily to fall into centralization. It doesn't have to be, but because zero-knowledge proofs takes a lot of time to be built, and to build such a proof, you need to understand what is the previous state, the previous block. Like imagine you are computing this proof, and by the time you're done, someone else have sent another batch to the layer 1. So the zero-knowledge proof is no longer valid. So you have collisions, and like you're wasting a crazy amount of resources. But still, the cool thing about the zero-knowledge proofs is that it makes the whole thing trustless, because it verifies the signatures and so on, which means that, that this operator cannot perform any action on behalf of the user. However, definitely there is some censorship vectors here, and the network could just be stopped if this operator falls down. So in order to solve this, we came up with this consensus protocol that we call proof of efficiency. And the main idea is to split the sequencing from the proof generation, and that actually enables a permissionless system that anyone can participate. So now the smart contract in this protocol requires to manage two different states. The virtual state, which is actually just the transactions, only the list of transactions, and then the consolidated state, which is adding the root, so proving the outcome of processing the transactions in the virtual batches. So actually, the virtual state is quite cool because since this is available on layer 1, anyone can synchronize this. So you could have your own node and understand this state update without the zero-knowledge proof at all. So you basically read the transactions from the layer 1, you process them, and then you have a node that understands what is the state, like the outcome of processing the transactions. And this obviously happens way faster than if you have to care about the zero-knowledge proofs. So then, like this rollup operator I was mentioning, it's also divided into different actors. First one is the sequencer. And so the sequencer just collects the transactions, sort them, and send it to Ethereum. As I was saying, this doesn't require to build a zero-knowledge proof. And hence, this process is quite fast. I mean, it's very close to layer 1 transaction fast, which is actually the better thing that a rollup has to offer because, I mean, the rollup is still inside layer 1. So we will not get faster than that, at least not in a super trustless way. And besides that, as I was mentioning, this system allows for permissionless, so anyone can participate at the same time. The reason behind that is that these transactions that we are sending don't know or don't care about actually processing them. It's like indicating to the network like, hey, you have to execute these transactions. But you don't need to know the previous state before sending the transactions. So here in the example, we have 3 sequencers that they are all trying to send these transactions. And when they send these transactions, they don't know at which position this virtual batch is going to be added. So it may be the immediate next one, or it could be like farther on. And by doing this, because the system is permissionless, we effectively decentralize the network. So it's no longer stoppable because, I mean, you can just, I mean, as long as you have access to Ethereum, you can keep adding these transactions. And also because of that, this became censorship resistance. Like, even if some sequencer was bullying you and blacklisting you, you could become a sequencer without asking permission to anyone and just send your own virtual badge into the network. And you may be thinking, then why to bother with zk at all, right? I mean, zk is very complicated, and it seems that we have everything. Well, this is not exactly the case, because the layer 1 doesn't understand the outcome of processing these transactions. And because of that, it also makes hard for the users, for the node operators, to know that they are actually in consensus. So how could, if I host a node, how could I know that everyone is on the same page? Well, if we have this zero-knowledge proof sent, we have the root on Ethereum, and I can just check if the root that I have built actually matches with the one on layer 1. And by the way, by having this, and by this I mean like the layer 1 being aware of the state on layer 2, we can build very cool things, such as on-chain bridge that relies exclusively on smart contracts. And like we all have heard like super sad news about bridges getting hacked. But if we are able to just rely on smart contracts, this gets more secure. And by the way, there is a very cool presentation by Jordi Bailina explaining it. If you are interested, you can just go to YouTube and search for Jordi Bailina at LeaseCon. Yeah, so how are these batches actually consolidated? Well, again, like the batches are on layer 1, so we have a new actor, which is the aggregator, which will synchronize the virtual batches to know which transactions are involved in the proof that has to be generated. And once the aggregator has that, it generates a zero-knowledge proof, and it just sent to the layer 1, to Ethereum, and effectively consolidating the virtual batch. So we move from the virtual state to the consolidated state. Unfortunately, this doesn't place that nice in terms of concurrency, because for each virtual batch, we have only one proof. And so the first one who sends the proof is the one who actually consolidates the batch. And so here what we expect that will happen is that the player, the aggregator that has the best technology will end up winning all the time, because this is not like proof of work that has some randomness built in. This is very deterministic. So if you have the best hardware, the best software, you will end up winning always. But this shouldn't be a problem, because at the end of the day, what happens with zero-knowledge proofs is that either they are correct or they are not. If they are correct, the network moves on. If they are incorrect, the transaction just gets reverted and has no effect on the state. And like even if we only had one player and this player just disappeared for some reason, anyone could come in again and become like another actor that still makes the network move forward. Yeah, so the overall picture looks like this. We have the sequencers sending the list of transactions that has to be processed, and they can make it in a concurrent way, so it's quite safe and fast. And then we have like the aggregators trying to have the best technology, the most efficient technology, and consolidating these blocks, or batches, sorry. So you may be wondering, why should people actually participate on the network, right? I mean, where are the incentives? And here what happens is that sequencers collect transaction fees, sorry, so the gas paid by the users. And so they are incentivized to build the most profitable batches, which means whoever is paying the gas at higher cost and whoever brings more transactions in a single batch. But then, what's in it for the aggregators? Well, the sequencers have to pay a collateral, which is a reward that will be collected by aggregators later on when they consolidate the proofs. And here what we aim for is, we don't have the final formula yet, but the idea is that the more unconsolidated batches there are, the most expensive is this collateral. And so the idea is that eventually we get into a stable point where there is no big delay between the virtual and the consolidated batches, because, I mean, it would be horrible if nobody's consolidating batches. So if apparently nobody's doing that, sequencer will just have to pay more tokens in order to be allowed to place these virtual batches in the first place. Okay, here's a bit more tricky stuff, more in detail. But this system could face front-running attacks, meaning that if you're a sequencer sending these virtual batches, someone could read this transaction from the layer 1 pool, just pay more gas, and make it before. And so effectively, the next batch, like the honest batch, will get fully invalid because the previous one will have processed all the transactions, and so the second time they will be just invalid. So in order to solve that, what we have done is we assign a different chain ID for each sequencer in a way that transactions are only meant to be included by a specific operator, a specific sequencer. So if anyone were to front run these transactions will be just invalid. In particular, the signature would not match, and so this will not have any effect at all in the state. And by the way, yes, it's a different chain ID, but it's still the same network. So you are not losing interoperability or anything like this. It's the same chain. Okay, so like this chain ID thing actually opens the door for new constructs that are quite cool. Basically, because transactions are meant to be included by a specific sequencer, anyone can become a sequencer, right? So what could happen is like you have a dApp and you instruct your users to use your own sequencer, which, by the way, right now is quite easy to do. I mean, you could just have a button on the UI, and then MetaMask pops up and say, hey, do you want to switch to this network? And, well, users say yes. And what this means is that the fees of the transactions of a specific dApp will be collected by the dApp itself, which in my opinion is great because sometimes it's hard for dApp developers to find a revenue model, or they have to come up with tokens that may not be very obvious in terms of utility. But by doing this, they are now able to collect the benefit of these fees. So if you are a dApp and you are able to bring transactions to the network, you will be rewarded by doing so. And by the way, being a sequencer, it's quite easy in terms of requirements. You need basically a layer 1 node and a layer 2 node, and that's it. You don't need crazy hardware. You don't need crazy staking. So the entry barrier for achieving this is quite low. And this is probably like the most basic use case that we can think of. But then things could get more complicated and more interesting. For instance, imagine if you have like a NFT marketplace that it already has great revenues by having a cut of the sales. And so this dApp, what could use is say, okay, I already have money, and then now I'm able to make transactions free for my users. And so the logic would like, if the transaction is directed to my smart contract, I will accept it, and I will accept it with gas fee 0, because anyway, I will later on be taking profit of this NFT sale or whatever. And I mean, this is probably not as easy as I'm explaining it. There are more challenges here, but we are starting to think on these different use cases that, I mean, we're excited to see what people could bring with this model. And yeah, that's it, guys. So maybe now we have some time for questions.
Thank you very much. Any questions from the audience?
Okay, thank you. Could you return to the slide with different sequencers? So when different sequences trying to send different transaction lists, yeah, these ones. So what will happen if two sequencers will send the same transaction, will include the same transaction?
Yeah, absolutely. So this effectively can happen. And what will happen is that only the first one will get executed. Because at the end of the day, executing transactions is deterministic. So like, this is bad for sequencers in this case because they will be including a transaction that later on will be invalid. And definitely sequencers would have to have kind of logic to avoid this. So like you have to take care of it and maybe try to ban bad users or whatever. But like, this will only happen if the user is malicious in the first place, because I mean, like if you are sending the same transaction to different sequencers, you are clearly misbehaving here. So this is a risk that sequencers have to manage, definitely, and it's a potential attack, yeah.
But do you already have the implementation of this sequencer or not yet? Okay,
so we are right now like developing like crazy, full speed. And like the zkEVM is not ready yet, but it should be relatively soon.
Okay, thank you very much. And also, I was a little bit confused about the part where like there is one validator that's basically doing everything because of the compute power. Why exactly can't he just like add some transactions that are malicious there, always verify them, and basically be like the main chain?
Okay, so here is where the zero-knowledge magic comes into place. So basically what you have is an off-chain computation that cryptographically proves that the transactions has been processed correctly, but then verifying this on layer 1, it's super cheap and fast. And so part of this logic that happens in zero-knowledge realm, it's to verify signatures. So,
but you're telling, so there are sequencers and then validators, how are they?
Aggregators.
Yeah. Aggregators. So the aggregators are doing the zk stuff, is correct?
Yeah.
Yeah, but they can manipulate not the zk proofs, but manipulate like what the blocks that they included over there.
Yeah, okay, so the idea here is that because the list of transactions that has to be processed, it's already on chain. So they have to wait for this data to be on chain, and then the smart contract ensures that only this data that is on chain is actually processed in the zero-knowledge proof.
But if, aren't there going to be competitions in like those batches that are already on chain? Or do you trust that all of them are non-malicious? Like, how exactly does it happen?
Yeah, okay, so, so sequencers send transactions, but there is actually no check at all at layer 1. So you could send like even a picture of a cat there, right? I mean, you can basically send whatever you want. But the thing is that if you send like incorrect data, incorrect transaction, this will have no effect at the time of processing it. So as I was mentioning, like processing this list of transactions have a deterministic outcome, and part of the checks that are done is like, is this transaction correct? Yeah.
Okay. Okay, interesting. But anyway, like the guy who chooses, okay, I need to do more research probably before making new questions.
I have a question. So how this consensus algorithm is like different from the Minas one? So where the sequencers or the block producers are chosen by the VRF functions, and then the snark builders are like doing the snark work. So the only reason that I'm getting here is that you are not the sequencers are not staking here. Mm-hmm. So what's the difference between like pros and cons, and why this?
Yeah, so I'm not fully aware of what Mina guys are doing, but basically here is permissionless, meaning that you don't require any permission at all to participate. It's kind of first in, first served, and yeah, you can just go in and as fast as you can.
Any more questions? Probably not. Thank you very much. Yeah,
sure,
it
thank you
was
guys.
really interesting.